so there's really not enough people for my taste, you know, because I had this, I had, every now and then when I do a lecture, I have, there we go, I want to also be in the movie. Every now and then when I do a lecture, I have an epiphany, and the epiphany gets me really excited, and then the lecture turns out to be really good because I got something I never knew before, and it's like, oh my God, I got to tell everybody. So that happened this week. Okay. Problem is that there's no everybody out there because where's my front row? So it's only like 8 of the 1, 2, 3, 4, 5, 6, 7, 8, 9. Last week there was 18. I wanted a couple more people. So I thought, well, there's a way to deal with that. I could bore you, the 8 of you, the 9 of you, with some facts, okay, which would be background facts that would be necessary to understand the lecture that I have. See, the lecture that I have really glosses over all sorts of facts in the interest of telling you the story. Maybe instead of that, I'll just spend my time not on the story, it's a good one, but the facts, you know, some facts, some things, and these facts are under the rubric, it's called astronomy, okay? So these are astronomy facts that, see, normally when I do this, I always avoid the mundane for the exciting. So with any help here, I'm going to go as mundane as I possibly can in the hopes that I will vamp until enough people show up in the cut. There's another person showing up. Vamp until enough people show up, and then I can start the lecture. So let's talk about let's talk about elementary particles. Okay, just a little bit. Just a little bit. Let's see where my stuff is. Elementary particles. Why? Okay, let me tell you what the topic is. Okay, the topic is that I'm not talking about today is called the Hubble Controversy, and the desktop image that I have on the screen is designed to explain that there is some problems with the Hubble constant and basically the expansion of the universe and the Big Bang in particular. And basically this is a fairly upsetting thing that's going on. So that's what the lecture is. That I might begin, because more people keep drifting in, maybe I'll just tell them that it's Monday and they'll come a day early, so show up. But so this is, the topic is, what? Okay, but we'll go back, we'll go to, just in the interest of just beginning to bore you with the things that you would need to know if I was just teaching you astronomy per se, I would, I would just do, just let's say, find you something to bore you with. Oh yes, that's good. So this is good to bore you with, because in fact, you're entitled to know these things, okay? You're entitled to know this, okay? This thing, okay? And what that is, let's see, what am I pointing? Yeah, okay. So what, this isn't the picture I was hoping for. But nevertheless, the words are on the screen. Let me turn off the light in the room. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's almost the quorum. And so we're going to be talking about the Big Bang, okay? And the Big Bang is all about the universe, and the universe is all about things that are in the universe. So I thought it'd be helpful just somewhat for you to know what the universe is made out of. Yeah, maybe. And this is one of those things that I, myself, never quite get right because I get some confusion in my brain. So I know that the universe is made, if you were born in my era, protons, neutrons, electrons, that's what you got, okay? But it turns out, of course, that the universe is made up of more things than that. Those are only one of those three are, if you will, fundamental. The other two are made up of other things. So that's the proton and the neutron. They're made up of other things. So protons and neutrons are made up of quarks. Okay, quarks. So before, in the Big Bang, before there were protons and neutrons, there were quarks. So quarks. But before there were quarks, I got to give you a name of something. There's something called hadrons. Hadrons are particles, okay, that are things, and those things are either baryons or mesons, okay? And you know everything about baryons. They are protons and neutrons and other stuff, antiprotons. Those are what you know. What you also know is something called leptons. And leptons are things like electrons and muons. Those things, you may have heard of muons. Okay, muons are hitting you all the time because there's cosmic rays, and cosmic rays come shooting down from the sky. They make your genes unhappy. They shoot cosmic rays through your body. Those are the muons that keep shooting through your body from the cosmic rays that impinge upon our atmosphere. Muons are your friends in the sense that they spend a lot of time in your body. And so we have baryons, and baryons are protons, and protons by themselves are not the fundamental particle. You got quarks. Okay, so when the universe is being made, the soup that it's made out of is made out of things that are pre-protonish and pre-neutronish. So, and those would be the quarks. Okay, so you need to know that, or not. Because in fact I was going to gloss over it, but because I didn't have enough people in the class, I thought I'd give you some facts. What? What are they? They're protons and neutrons. Oh, you want to know what they are?
What, the quarks?
Yeah. What do you mean? What are they?
Anything smaller than a quark?
There's nothing small. Well, quarks aren't small. Electrons are small, and even smaller than electrons, and not on this list of things that I just mentioned, are neutrinos. And neutrinos are of an extremely small nature. They have the ability, built in at birth, to travel through you without touching you. They can go right through you and keep right on going, and your body won't even notice it. There will be no collisions. In fact, in order to stop a neutrino, what you do is you order a light year's worth of lead, okay? 1 light year worth of lead, and you shoot the neutrino through the light year of lead, and you have a 50-50 chance of having it hit something in that light year's worth of lead. It's really a particle which doesn't want to be stopped. And but nevertheless we're able to measure them because what we do is, since there are trillions of neutrinos flowing through your body every second, even though a given one won't stop, statistically, if you have trillions floating through you, then after a certain period of time, one of them statistically will stop at you, and you will be neutrinoized. No such word. So what they actually do is they put a neutrino detector at the bottom, 1 mile down in a mine, so that basically nothing hits them except neutrinos, which can penetrate deeply. And so a mile down, they have a neutrino detector, and they detect neutrinos, and they count them, and they tell you stories about them. And one of the stories, there are 2 stories. One of them is that neutrinos are extremely not massive. They hardly weigh anything. Almost no mass. They have very little mass. They have so little mass that we only have constraints on it rather than a number. We have it's about this big, but usually particles, we know exactly what mass is. Neutrinos, we just have an idea. We know they're not massless, which is as good as it gets, and therefore they can't travel at the speed of light, but they can penetrate like crazy. And the other thing about neutrinos that's really interesting is they come in three sorts. And these three sorts of neutrinos are new in the sense of we didn't see these coming, because what happens is the sun makes neutrinos. So we put a telescope at the bottom of a mine down somewhere in South Africa, I forget where, and we measured the neutrinos that came from the sun, and the neutrinos that were coming from the sun turned out to be not enough. And if you don't have enough neutrinos coming from the sun, then there is the worry that the sun is not making enough sunlight at the very bottom of where the neutrinos are being generated. And so after a certain period of time, like 1 million years or something, when the sunlight finally gets to the surface, the Earth will suddenly not get enough sunlight, and that could be bad for us. So there was the neutrino, I don't know what they called it, disaster. The sun could have been going out. We were concerned, and people got really concerned. The neutrinos level was not good enough. And then somebody said, but aha, your detector is only good at detecting this kind of neutrino. I'm not going to name it because I forget the name. Tau neutrino. And there are three kinds of neutrinos. So what happens is, while a neutrino is on the way from the sun to the Earth, it changes who it is. It becomes another kind of neutrino, and then another kind of neutrino, and your detector can only detect one of those neutrinos, but not the other two, so you're missing 2/3 of the neutrinos. So guess what? It's not a problem. You got the right kind of neutrinos. Point isn't, and this is why do we need to know this for the story I'm going to tell you later? Because the thing you need to know for later is that there are three kinds of neutrinos. Only three kinds of neutrinos. Not four. Three. So that could be useful later on in the conversation, which at this point is now 1, 2, 3, 12 people. Still not sure I want to begin that lecture. Okay. Let's see what else I can tell you about things that you would need to know if I was actually telling you the lecture.
What do these things do for us?
They don't do anything for us.
Why do we need them?
We don't need them.
So why are we talking about it?
Oh, well, we don't need them, but the lecture does. Okay? You need to know that when I tell you later on in the lecture that one of the ways to solve the problems that are being discovered is to postulate 4 kinds of neutrinos. Okay? Now, Elaine, you know, and you're always here, and Howard for that matter also, is always on the level of new physics, things that we don't know. Okay? So this lecture was supposed to be, it may still be, about things we don't know, and for which the data is saying you better pay attention because this is a mystery and you should solve it. If you are the astrophysicist, then you've got to come up with a solution. And one of the solutions to the mystery that I haven't presented yet is 4 types of neutrinos, not 3. But everybody knows there's 3. Okay? So it would make you happy, Elaine, if there were 4 kinds of neutrinos, right? Because they would go, oh, something new in science, not the same old stuff.
Why would that be good?
Why would it be good? Because what is your ongoing question in this class? You have an ongoing question. You ask the same question over and over and over again in different ways. So what is the question that you ask?
What is the universe?
No, Elaine's question, not yours.
What's it all about? Ouch.
What's it all about?
No, I don't know. It seems to me like what you want to know is you want to know the big picture.
Yeah.
You want to know the big picture, right? You want to know. It's not okay for you to know about planets. You don't care. Stars doesn't float your boat. What you really want to know is the whole universe. You want answers like which explain the whole universe.
That's
So,
what I asked.
oh, what did you say? Because I wasn't
I
listening.
said, what is the universe?
What is the universe? Right. So I'm sorry. Yes, you asked the same question. So, so that's the question in this class that I don't answer. Okay. So that is an approach to this. But in order to do that, we need to know if there are 3 or 4 kinds of neutrinos.
3 or 4 kinds of neutrinos.
Right. And right now I'm telling you there's only 3. So on the basis of only 3, we have a mystery, which I haven't explained yet. And I'll keep foreshadowing that until maybe the class is over, or maybe I'll begin the lecture. But in the meantime, I'm just going to go back to my idea of just talking about things that you don't know that I could just gloss over in the normal lecture, which I will try not to do. Okay, so let's see what other things could be. Oops. Okay, so other things that would be useful to know if I wasn't glossing over them. That would be useful to know in order to understand the controversy that is represented by the picture. This picture,
Of the universe.
this picture of the universe is what we're talking about. The question, that's the question. Okay, so other things that you need to know that you may not know. Okay. Okay. Who knows? Well, okay. Who knows what a white dwarf is? I mean, as in the sense of why do we have white dwarfs and why are they?
They're
Okay.
dying stars.
The dying stars. Dying stars. How did they get dead?
They lost their energy.
They lost their energy.
They collapse.
They collapsed. Okay, so collapse is the right answer. But they collapsed because what happened was they ran out of fuel. They see because our star stands there, all happy, and it's as big as our sun, and it continues to be as big as our sun because it can do that for millions of years. In fact, it can do it for billions of years. It can do it for billions of years. It can continue to be our sun for billions of years, doing what it does, and over time, getting a little bigger, and then a little bigger, wider, not bigger, no more mass, just wider. And over time, a billion years, it can start to get so wide that the sun becomes so bright in the sky that you wouldn't want to live on Earth anymore. So if Elon Musk has a project to move to Mars, that would be the right time, about a billion years from now. Okay, and that would be a good idea. You move to Mars a billion years from now, the water would melt, the atmosphere would fill up with gas, and you could live on Mars. But that's a billion years from now, not now. After that, the sun is becoming a red giant. When the sun becomes a red giant, it becomes bigger and bigger and bigger, and pretty soon the orbit of Mercury is subsumed. Mercury ends up sitting inside the sun. You can know what's going to happen to that. It's going to fry and just evaporate into Mercury particles. And then eventually Venus gets in the way, and Venus gets sucked into the sun. And there's a possibility that even the entire Earth could get sucked into the sun. And then we're gone. Long before that, we're burned up, but we're gone. And then the sun, having done its red giant thing, blows off its envelope, can't hold itself up anymore, shrinks down into a white dwarf, and you get a white dwarf. And white dwarfs are useful if you want to figure out how the universe works, because white dwarfs do one thing that other things don't do very well. They can be made to explode if you do it very carefully. So how do you carefully explode a white dwarf? And I say carefully because If you just blew the things up and they just went boom in the sky, then that wouldn't tell you anything. You need to know something about the explosion to be able to use it in some way to help understand the universe. What you want to do is you do this. Okay. So here you have, first of all, you need two stars. Okay, two stars. One of them is slightly bigger than the other. Okay, this is the big one. This is the small one. Okay, this one gets, because it's bigger, it also lives fast and furiously and gets bigger, wider, faster. So it gets bigger and bigger, and when it gets to be this big, okay, it starts to get big enough that this star starts to take some of the gas from the red giant, and it starts to flow into the little star, which by now has also done its thing. Now this is a white dwarf. So this little star is a white dwarf, sitting there happily being a white dwarf. Okay, this big star is shedding its outer envelopes, and the little star is sucking it up piece by piece.
How does something become a red giant? Does it eat up other?
No, that's a good question. How does something become a red? See, I am still glossing over things like an entire field of astrophysics, right? So glossing over, without glossing over, how does something become a red giant? Okay. The interior of the star is what its business is to make, via fusion, to make light. The light that it makes, the energy that is emitted from the center of the star where the nuclear fusion occurs, goes out and holds up the star from falling in on itself, because the radiation pressure and the light pressure keeps it up. So the star stays up, the thing in the center keeps it up, and it's a contract between the outside and the inside. But when the inside starts to use up its nuclear fuel, which happens because the nuclear fuel is hydrogen, but when it starts using up too much of its hydrogen, you get only helium. Then helium doesn't fuse at the same temperature, and the inside of the star needs to contract in order to make the center of the star hotter, so helium can burn, so that the outside layers can stay up. So, but when that same thing happens, when the helium starts burning for some reason that I can't easily explain, the outside layers get bigger. At the same time that the inside gets smaller, the outside gets bigger. So the outside gets puffed up, and every time the inside gets smaller, the outside gets bigger. But no change in the mass, just change in the diameter. And they didn't really explain why the outside gets bigger, because I don't understand it.
So as the outside gets bigger, is the red giant actually thinning out?
Yes.
Like a piece of elastic?
Yes. It's thinning out so much, in fact, that there are red giants that are as big as our solar system. So the one star is as big as our solar system. Okay, but it's only 10 times or maybe 100 times more massive than our own sun. So if you spread that much mass over the entire solar system, then you get
A pancake.
not a pancake. You get a very, very tenuous gas that you couldn't even tell you were flying through, except for the fact that it would be sort of noctilescent. You wouldn't be able to see very far, but you'd be in a cloud. You'd be able to put your hand in front of you, and although the temperature would be millions of degrees, well, thousands of degrees, it wouldn't be hot, because there's the difference between hotness and temperature. this room is both warm, and it has a temperature, and it's hot. If I took this room and we went way higher than Mount Everest in this room, and I heated it to the same temperature as this room, you'd be cold, because there's not enough air in the room to impinge upon your skin to keep your skin warm. So although the temperature would be warm, the molecules don't heat you up enough. So you'd be cold because there's not enough heat, even though the temperature. So you can make millions of degrees out of something and still have it be not hot. So the outside layers of the star, while have a very high temperature, wouldn't be hot. And so if you were traveling through the outside layers. So, but nevertheless, the star itself is making enough heat overall that it could fry anything. It's just you have to be standing outside of it, if you will, and you're getting blown back by the light rays that are coming at you, which is called radiative heating, rather than being warmed up and nice and cozy by the molecules around you, which is called convective heating. You know that you stand in front of a fire on a cold night. One part of you is nice and toasty, another part of you is freezing cold. That's radiative heating. You can get really, really hot, okay? But the and this is where the analogy fails. You still don't want to put your hand inside the fire, because the fire also has enough molecules to burn your hand.
So every white dwarf is formed from a red giant's
Yes.
proximity?
No, I may have confused things in the interest of keeping you amused before I begin the lecture. So no. What happens is, I did not say, but what happens is the red giant eventually blows off all its outer layers, leaving behind a white dwarf that is no longer making any nuclear fuel. It is not fusing atoms into higher level elements. The helium is burned up, the carbon is burned up. It can't get hot enough to ignite the iron or the nickel. It runs out of fuel, and it can't make it any hotter, and it says, I'm done, I'm finished, this is where I stop. And it stops. By the time the red giant finishes its business, it's down to something that is around the size of mass of our sun and about the size of the Earth. So a white dwarf is about the size of the Earth, and it's about the mass of the sun. That's where the good stuff starts. From the point of view of the controversy of what's happening in the universe, because white dwarfs are one of the keys that we use to investigate the universe, oddly enough. Because back here in the diagram, we have this red giant, which is throwing off all its gases, and this red giant, which became a white dwarf. So this white dwarf is getting gases from this red giant. Bit by bit by bit is dropping onto the surface of the white dwarf. However, there is a rule in nature, and it is one of nature's, I think it's nature gives you gifts along the way so you can investigate nature. And if this wasn't a gift of nature, and I could say God, but you know, the gift of nature is that you can't build a white dwarf any bigger than 1.44 solar masses. The laws of nature say that's it, you're done. You can't get anything bigger than that. So what happens if this red giant is still, which didn't get the memo, okay? If this red giant is continuing to shuffle off gases onto that white dwarf, what do you get? You get a supernova. And this thing blows up. And it becomes brighter than the entire galaxy, in which it lives for a few weeks or months, this becomes the brightest thing in the sky. We've seen these with the naked eye 400 years ago. Naked eye. They call them nova or supernova. They've been seen by the Chinese in 1066, I believe. They've been seen by the Native Americans, have put a paleoglyph on the stone that shows a supernova in the sky that they saw. The Chinese saw it. The Europeans saw it. We haven't seen one in our galaxy in 400 years. But they come around every 100 years or so. So if it's lucky, before you all die and I die, maybe we'll get to see one. Hopefully not too close, because if it was close, it could do major damage. And I mean severe damage to the Earth. It could wipe us out easily if it was near enough. But chances are, statistically, it won't be near enough. It'll be far away, and it'll be just a lot of fun to watch. And I'm always hoping for one. You should hope for one too. They're better than comets. They last for weeks, and you can see them during the daytime, for God's sakes. That'd be wonderful. Assuming they're close. Okay? But why do I care about 1.44 solar masses? What's the big deal? The big deal is that every supernova that explodes like this, and there are other reasons why supernova explode. This one is called a type 1A supernova. It's actually got a name, type 1A. There are type 2s, there are type 1Bs, there are different kinds of supernovas. But this supernova is unique because it's the same supernova over and over and over again, which means its brightness is the same. If you were standing a known distance from it, you could say, oh, I see it. Well, if it's further away, it's dimmer. Closer, it's brighter. But it's exactly the same supernova at different distances. So whenever one goes off, you know exactly how far away it is. That's terrific. It can give you a way to measure the distances to things, because if you already know how bright this thing is to begin with, and that, by the way, is not something you know intrinsically, comes from other answers. But if you know how bright this is to begin with, then you can use it, and this is the word that is also on this screen over here, which you can't see if you're looking elsewhere, is standard candle. Standard candle is what a supernova is when it's a type 1A supernova. It's reliable. You can use it to measure the universe. Yes.
Are you saying that every supernova has the same brightness?
Yes, every type 1A supernova has the same brightness. Yes. But there are different supernovas with different brightnesses.
Right,
Right.
but I'll accept just that beginning.
It's terrific. And if you will, there are other supernovas, by the way. We have a black hole aficionado in the group. Yeah, that's you. Okay, that's you. Let's say you are a black hole enthusiast. Okay. What you need, if you're a black hole enthusiast, you would like this thing to turn not into a supernova, but not just any supernova, but a black hole. You'd like a black hole coming out of this. Because what happens out of this is, if it's the type 1A supernova, all you get is a neutron star, a puny little neutron star about the size of Manhattan Island, with the mass of our sun, or some percent of the mass of our sun, in something concentrated as small as Manhattan Island. That's on your way to a black hole, but it's not a black hole. You want to make a black hole? Don't fool around with type 1A supernovas. Just make a big star. You make a big star bigger than, say, 10 solar masses. In the universe, stars can be only certain sizes, and really big ones have a habit of exploding, and even small big ones have a habit of exploding. And what they do when they explode is they make black holes. So we got lots of black holes scooting around in our galaxy, caused by supernovas. But this one, the one that I care about here, doesn't make a black hole. Okay. So, what else do I want to talk about that doesn't include the topic that I prepared for the day?
Dark energy, string theory.
Dark energy, string theory, it's up there on the screen, but I don't want to talk, I could talk about dark energy a tad. Yeah, okay. I could talk about dark, so. So I had a professor at Cornell. His name was Tommy Gold. Tommy Gold. He was Austrian. He was head of the astronomy department at Cornell. He was the one who, in fact, was responsible for hiring Carl Sagan to come to Cornell. He was also my thesis advisor for a year. And he was a nutcase, real nutcase. He didn't think that it was necessary to know how to do math in order to do astronomy, which in my case was wrong, because the only reason I could do astronomy was because I could do math. He could do astronomy in his head. He had a working universe in his head, he used to say. And he would, from time to time, consult his working universe to determine how things worked. And you have to say that he was sort of right and sort of wrong. He was 50-50 on a lot of things that he got right and he got wrong. For instance, before we went to the moon, it was Tommy Gold who said, "Excuse me, you might sink in to the moon because it's covered with dust," okay? And they called that dust, because his name was Tommy Gold, they called it gold dust. Gold dust. There's gold dust on the moon. And he even designed an instrument which the astronauts took to the moon to examine the gold dust in situ. So he had a device that literally you put down on the ground so you could measure, take a wide angle but narrow angle, close-up photograph of whatever there was. He was afraid that people would sink into the moon. The first spacecraft that went to the moon, they took pictures of their feet, because their feet would tell them exactly how deep they sunk into the moon, into the gold dust. And Tommy Gold was afraid they'd sink all the way through, and then the thing would not even be able to pop out and never take off again. And besides, you couldn't exit the spacecraft because you'd be inside of a fairy castle of moon dust. But that turned out not to be true, of course. But they did sink into the ground. And when they took pictures of the first footprint that they ever soft landed on the moon, the first picture they ever took was of the footprint, because they wanted to see how deeply it sank. And I stayed up to 4 o'clock in the morning once to watch a footprint on the surface of the moon. And believe me, it was exciting. And it was exciting for Tommy Gold as well, who was a couple of offices down, because it was his idea. Turned out to be not so right, not so wrong. It was okay. The moon was covered with very fine dust. He predicted that. But one of the things that he predicted that was not so quite right was, I guess I'm straying into the topic that I was trying to avoid. I'll try to tell you as little as possible. He predicted that the universe was going to expand forever, which is okay, it's true, but that it always had been expanding forever. He predicted that the universe now is exactly the same as the universe then, no matter how far back in time you went. So he got his name on the steady state theory of the universe. And he and his buddy, Herman Bondi and Hoyle, got to deride this theory out there. He called it, Tommy Gold called it, the Big Bang theory. That's crap. The Big Bang, there's no Big Bang, it's obvious. The universe is now the same as it always was. And I will try now not to tell you how come he got to be wrong, because that would be straying into my lecture for next time. Okay, so, but so there is not just one version of how the universe goes. There's actually another version, and that version was not settled until after you guys graduated college. Okay, they knew the universe was expanding. They didn't know whether Tommy Gull was right or wrong until after you left the source of your major education. And I assume everybody in this room, of course, has been to college and graduate school for that matter. How many people in this room have been to graduate school, not just college? That's a majority. It's interesting.
Laird,
Yes.
has anybody called the situation the steady state?
Has anyone called
instead of Big Bang?
the steady state theory of the universe is Tommy Gold's idea, as well as
Not true?
it's not true.
Oh, okay.
It's not true.
No, I don't want to ruin your lecture.
Don't ruin my lecture. Go ahead anyway.
Huh?
No, go ahead.
The background radiation that's omnipresent took away that theory.
Okay, see, Howard ruined the lecture just now. Okay? He did. He absolutely did. I won't even repeat what it is you said for whoever's going to watch this on the web. Yes, you're absolutely right. and he literally didn't buy it. I mean, he saw how important that was, and so he's like, nah, that doesn't count. It's not important, But because you did mention that, whatever it is that you mentioned, I will mention this thing called Blackbody Radiation, okay, which is another one of those things that it would be good if you knew it, so that when I glossed over it next week, you would know more about it than you do now. Okay, so there's this thing called, yes.
Question to the steady state. I thought that was before they knew that it's expanding.
No, this was after they knew it was expanding.
It's still steady state.
Yeah. No, I forgot to say. So the reason it has to do with dark energy, I forgot because that's what started me on this. The reason it has to do with dark energy. In order to have a steady state universe, what you have to do is you have to, in the middle of nowhere, you have to create things from nothing. The universe has to create matter from empty space. Okay? So Tommy Gold said, well, then that's it. The universe creates matter out of empty space every now and then in, a light year or 1,000 light years of empty space, a single proton appears out of nowhere. That was necessary for the steady state theory of the universe. He needed that. And, of course, that's not true. Now we have something called dark energy. And from the middle of nowhere, we have energy appearing out of nowhere. Okay? So while his idea, his insane idea of that matter would be created out of nothing, what we have now is energy being created out of nothing, and that's okay. It's just Tommy Gold's idea of matter being created out of nothing turned out to be hokum. So, I mean, the guy had brain. The guy he could see things. He understood that there were possibilities that went beyond what people thought. He also, some of his other ideas, which were totally hokum, but I don't know that they're hokum exactly. He thought that all fossil fuel was made not by biological life. He thought it simply was carbon seeping out of the earth, because there's enough carbon inside the earth to make fossil fuel. The only question is it hydrocarbon? which you can burn. Carbon is clearly in the earth everywhere. We're made of mostly carbon. It didn't come from the sun. It's been here all along. So the only question is, did the earth make hydrocarbons without sunlight? And according to Tommy Gold, yeah, it is. So therefore, if you can go drilling anywhere on the earth and you'll find oil. So that was Tommy Gold's idea. Oil everywhere on earth. And he actually went drilling. He did. He got the United States government to drill in, I don't know, Russia. He dug holes looking for his precious oil. He said, and some of that's true, he said, you know what? The seafloor is covered with methane. You could go down there and you could mine the methane. It turned out to be right on that. The seafloor is covered with methane. Methane hydrates, I think they're called. And in the tundra you've got the methane buried. In the seafloor you've got the methane buried. You go dredging that stuff up, you're going to get more global warming than you ever could count on. So he had that one right. He also came up with why does the sun explode every now and then and you get solar flares? It was Tommy Gold who said, I can explain to you how solar flares are created. Does anyone want to listen? And nobody wanted to listen. But he turned out to be right. The way solar flares happen is you have these magnetic fields on the sun, and there's a north pole here and there's a south pole here, and those are sunspots right underneath my left and right arms. And what you have in the middle is magnetic field lines that run from here to here. So magnetic field lines, and there is plasma between it, running along the magnetic field lines, right, like this. And sometimes the magnetic field lines cross, and then they break, and that creates a solar flare. And that was Tommy Gold's idea, and that was a good one. So he just got a few things wrong, a few things right. And he was difficult to work for. What we did for me is, he said, Laird, I want you to prove that Venus used to have oceans. And I spent a year working that out, okay? Getting nowhere. He said, the sun blew off the water from Venus, and that's why there's no water on Venus. So go explain how that could have happened, Laird. And there was no way I could do that. Because that requires a lot of math, and I wasn't about to try the math. The math is called magnetohydrodynamics, and I would have had to invent it out of whole cloth, and I didn't feel like it. So I just researched the thing for a year. And then Carl Sagan came. And then Carl Sagan said, I can work for you. So I said, Tommy, thanks a lot, and I'll see you. But Tommy used to take me water skiing, which is terrific. He used to take. He had a 100 horsepower boat, and he would have me drive the boat, and we'd drive up and down Cayuga Lake because he had amazing thighs, and he let me. He even taught me how to get up on one foot. You put your foot down, and with the other foot, because he's Tommy Gold, he said, make an airplane wing. He said, make an airplane wing. And with the other foot, you can have that foil, and that airfoil, which you use from the other leg, will get you up. And sure enough, it did. So, yeah, and so that's how I learned how to water ski, Tommy Gold.
How about the Planck satellite?
Oh, Planck satellite, we're getting to next week.
Okay.
Planck satellite is, I'm keeping that a mystery. It's on the screen, but I didn't discuss it. We'll discuss Blackbody radiation, okay? In the few remaining minutes, just some of it, okay? Blackbody radiation. What's a black body? Why do you care? You're a black body, okay? You're a black body, but you're not a very good black body. On the other hand, if I take a device that I purchased from the hardware store and I point it at you, okay, I can measure your temperature from across the room because you are radiating heat. And if I get really close to your forehead and I point it at your forehead, it'll say something like 90 or 95 degrees. If you point it in your ear or up your mouth, it'll say like something like 98 degrees. So literally, you are a black body in there. This is what a black body looks like, in the sense of that's what the data would be. So here at the bottom, you can see the wavelength of light, and they've been so generous as to color it. So 600 nanometers, which is a wavelength of light, is around yellow, and 700 is around violet, and ultra infrared, and 500 is around ultraviolet. So this is the visible spectrum. This is the visible spectrum from one wavelength to another wavelength. This is how much radiation is emitted at any given wavelength. So at this wavelength, there's this much radiation. At this wavelength, there's this much radiation. At this wavelength, there's this much radiation. This is the temperature of our sun. What do you notice here? And the answer to my rhetorical question is, what you notice is that the colors that we see are exactly near the peak of the spectrum that our sun emits. So our sun, we adapted to be able to see most perfectly the light from our own sun. The peak is where we see. Some suns are of different temperature, and they have a different black body temperature. So let me make a sun that has a different black body temperature. For example, some suns are very, very small, and they are very, very red. And if I make a very, very red sun by turning the temperature down, I've turned the temperature down now to a very red sun, and you can see that the peak is way off in the infrared where we can't see. And so what we can see is only very little of the light that comes from a red sun. Because a red sun's black body temperature is 3,000 degrees Kelvin, which is a version of centigrade, and it looks dim to us, but it's actually quite bright, but we wouldn't see it that way. If we were standing in front of it, it would look kind of dim. Some suns are very, very bright. They're white hot, and those suns have a surface temperature that is very hot. And those suns, their peak is way off in the ultraviolet, and we can't see those either. So although we would be able to see the sun, we would be missing most of the light. So if we had evolved around a sun like this, we would be seeing in the ultraviolet. And if we had evolved around a sun like this, which is very cool, we'd be seeing in the infrared. These curves are called Blackbody curves, and they indicate and they tell you the kind of heat that's emitted from various black bodies. Okay? Next week, we're going to talk about the biggest black body in the universe, which is the universe itself, which is also a black body, and much cooler than this.